Today's topic is dispersion in conductors. Previous topic we did the dispersion in non-conductors. This one topic we will be discussing the how dispersion takes place in conductors. What are these factors which are responsible for the dispersion? The topic code is EMWD-S3. The free electron in the conductors are not bound to any particular atom or molecule. Nevertheless, essentially the same model, that is electron model, can be applied. In the non-conductors we see that they are bound to the atoms, but in case atoms are the nucleus, the in case of non-conductors, but in conductors we have electrons are free, not bound to one particular molecule or the atoms. So, but anyway, we apply the electron model can be applied to them if we set the binding force equal to 0 and consider that the damping factor gamma is attributable to the cumulative effect of many collisions is relatively large. Now, the equation of the motion takes the form as d2y by dt square is equal to f damp plus f driving. So we neglect the binding force in this case. So putting these values, we get the adding all these together, rearranging the equations. d2y by dt square plus gamma dy by dt is equal to q by m e naught e to the power minus I omega t. Again, obviously this is the damping force, which is minus mk dy by dt, and the driving force is q by m e naught e to the power minus I omega t. Since the displacement y is given by y naught e to the power minus I omega t, so taking again the differential with respect to time, we get minus I omega yt, and second differential of the y will give us the minus omega square y naught e to the power minus I omega t. Now putting these values in equation number 1, we have the magnitude y naught is the magnitude, the amplitude. This is amplitude y naught is given by minus q by m omega square minus I gamma omega e naught, which is the amplitude. This is equation number 3. This time we are not interested in the polarization associated with the electrons, but rather the current they generate. Okay, so the current density J is given by nfq dy by dt. You can get the where n is the volume, you can see density, number of all the electrons per unit volume, and J is the current density. If you put that, you get the dimension of the current density in this case. So where F is the number, if F is the number of the free electrons per unit volume, then eventually J is the real part, while the J tilde sign is a complex part. The complex J is of the form J complex is nfq dy complex by dt. Equation number 4. So from equation 2 we have dy by dt is equal to this term. So putting that term in equation number 4, we get J is equal to nfq times q by m gamma minus I omega e, which is the complex function. The imaginary term of equation 5 in the denominator means that J is out of phase with E, that is the current is not proportional to the field, which means this material does not, strictly speaking, obeys the Ohm's law. However, the fact that the complex current is proportional to the complex field, which suggests us to introduce a complex conductivity as well, with J, complex J is equal to sigma c, which is complex with the tilde sign, the complex conductivity with times the E field complex function. So putting the J from the equation 5 in equation 6, we have sigma c is equal to NFQ square by m divided by gamma minus I omega. This is question number 7. But for sufficiently large frequencies, the phase difference between J and E cannot be ignored. In fact, the current cannot keep up when the driving force oscillates too rapidly. So naturally, all this effect, all this if these effects, all this affects the behavior of the electromagnetic waves in a conductor at higher frequencies. So let us now take the complex conductivity equal to the real part and imaginary part, two parts, which is the sigma r, which is the real, r for real, plus I sigma I, which is the imaginary. Rationalizing the equation 7, we get sigma c is equal to the real part and an imaginary part. Equation number 9. So comparing the real and imaginary part, what we are we have the equation 8 and 9. If we compare these two, sigma r, the real part, is given by gamma n f q square by m, gamma square plus omega square, and the imaginary part, the conductivity, is given as omega n f q square by m, gamma square plus omega square. Hence, for real j is equal to sigma r e, which is equal to j is equal to gamma n f q square by m, gamma square plus omega square e. So hence we worked out the relationship which for the dispersion of the incoming electromagnetic waves, the responsible factors, we worked out that the conductivity is the, you can see here in this case, is also playing important role, and the dispersion of the waves takes place in the medium, in this case the conducting medium. Okay, with this we reach to the end of this topic, and inshallah we will meet again next time. Thank you.